In this example, we're actually going to evaluate one of these surface integrals. For this one, I'd like to evaluate the surface integral over the surface S of xz ds, where S is the portion of 2x plus 2y plus z equals 4 that lies within the first octant. So the first thing we're going to have to do is parameterize the given surface. And in parameterizing the given surface, I think a visualization would probably be handy to have. Now the portion of this plane that lies in the first octant is going to be a triangle. We can figure it out by getting the intercepts for the given plane. So 1, 2, 3. Z-intercept is 4, x-intercept is 2, and y-intercept is 2. So we get this nice little isosceles triangle within the first octant, and that is our surface S. So I think what I'd like to do is express z as a function of both x and y, and we'll allow the corresponding projection into the xy plane and be our region D. So to parameterize the surface, we'll let x be equal to u, we'll let y be equal to v, and we'll let z be equal to, if we solve this, that'll be 4 minus 2x minus 2y. Now there is a shortcut for when we're using z as a function of x and y to figure out what ds is equal to. So if you want to, you are welcome to use the following shortcut. I, however, would like to show you where it comes from as we do this example. Quantity squared dA. So I'm actually going to find our partial derivatives and see if we can't derive where everything comes from. So my parametric surface, R of u and v, is going to be equal to u, v, 4 minus 2u minus 2v. The partial derivative of r with respect to u is going to wind up being equal to, with respect to u, we'll be treating v as a constant. That'll be 1, 0, and negative 2. For the partial derivative of r with respect to v, we'll be treating u as though it's a constant, so 0, 1, and negative 2. So with those things in mind, let's take a cross product, and then we will find the corresponding magnitude. So across the top row, I, j, k. Second row is going to be 1, 0, negative 2. Across the third row, 0, 1, negative 2. Recopy the first two columns here and give it some slashes going in the downward direction. For the I component, there's a 0 on there, so we'll call that 0I. For the j component, there's a 0 on that line as well, so 0j. And for the k component, I'm saying 1 times 1 times k. It'll be 1k. On the negative side of things, for the k component, I'm seeing 0k, and that's okay. For the I component, I'm seeing negative 2i, and for the j component, I am seeing negative 2j. And once again, for the trained eye on this one, the result that we get is 2, 2, 1, which happens to be the same as the direction vector for the given surface. So not a coincidence that it happens to work out that way. So as far as ds is concerned, we're going to take the magnitude of this cross product, and you'll notice that the three components that we get here are 2, 2, and 1, which again correspond to a 1 followed by the partial derivatives squared. So 2 squared plus 2 squared plus 1 squared, dA. Ooh, made that a little long. Oops. So we'll refer to that as 3 dA. Additionally, our region D is now going to be parameterized in the following fashion. We referred to x as u, we referred to y as v, and this would technically be the line if we make these substitutions. 2u plus 2v is equal to 4. That is to say, back up in the original plane, we set z equal to 0 since we were in the xy plane, and then substituted in x equals u and y equals v, that would take us to this. Or if we wanted to be more succinct about this, we could also say that u plus v is equal to 2. That'll look nicely as either a type 1 region or a type 2 region once we parameterize. So the original surface integral was surface integral over s of x z ds. We are now ready to parameterize. We'll refer to this as the double integral over d, where this is our region d. X we said is going to be equal to u. Z is going to be equal to 4 minus 2u minus 2v dA. Now we can make a judgment call as to whether we'd like to integrate with respect to v first or with respect to u first. I think I'd like to go with respect to v first. So we'll express our region as a type 1 region. We'll see that v is bounded below by the u-axis, which would be v equals 0, and above by this line, so we solve the line for v. That'll be 2 minus u. U will then go from a constant to a constant, and that'll be from 0 to 2. So at the next step, I'm going to distribute the u and actually plug in these bounds. So once again, 0 to 2 and 0 to 2 minus u of 4u minus 2u squared minus 2uv. And we're going to go dv du. Everything that we're going to see hereafter is going to be simply the power rule, so let's not fret too much. Let's integrate with respect to v. Actually, before we integrate with respect to v, I see us running out of space here. So let's go ahead and do the following. And hopefully we'll be able to continue this on to our next page. So integrating with respect to v, 4u is a constant, so that'll be 4uv. 2u squared is a constant, so that'll be 2u squared v. And for 2uv, that'll be uv squared, going from lower bound 0 to upper bound 2 minus u. And after that's done, we'll be integrating with respect to u. Plugging in these bounds, the lower bound is going to give us a lot of 0. The upper bound is going to replace all of the v's with a 2 minus u. So this will be 4u times 2 minus u minus 2u squared times 2 minus u minus u times 2 minus u quantity squared du. I think we can now make the transition onto the next page. And we will need to do some distributing, foiling, all sorts of good stuff. We'll still have the definite integral from 0 to 2. Distributing the 4u, we'll get 8u minus 4u squared. Distributing the minus 2u squared, that will be minus 4u squared plus 2u cubed. And then this one's going to be a little bit trickier. We need to FOIL this, and we'll be distributing a minus u after that. So let's do that in 2 steps. Don't want to do too much at a time. So with all of that in mind, let's go ahead and distribute this minus u. Then we'll worry about combining like terms and then integrating one last time. So 8u minus 4u squared minus 4u squared plus 2u cubed. So that'll be minus 4u plus 4u squared minus u cubed du. Now we can worry about combining like terms. We'll start with the u cubeds. I'm seeing 2 of them here minus 1 of them here. That'll be u cubed. For the u squareds, we can cancel out a minus 4u squared with a plus 4u squared. That'll give us minus 4u squared. And we'll have an 8u minus 4u. That'll be plus 4u. I just realized throughout this entire process, I don't believe that I ever accounted for the 3 that we had for dA back here. So this should be 3 dA, and then we'll just move the 3 to the front for the rest of the steps. Wow, this is going to be a real bummer for anybody who was screaming at the video for the last 5 minutes. What about the 3? Yeah, should have accounted for that. My bad, guys. Integrating with respect to u, we'll get 1/4, u to the 4th, minus 4/3, u to the 3rd, plus 2u squared, going from 0 to 2. This 3 will cancel out with the other 3 very nicely in just a moment. So this will be 1/4 of 2 to the 4th power, minus 4/3 of 2 to the 3rd power, plus 2 times 2 squared, minus a whole bunch of 0. Continuing to simplify, 2 to the 4th is 16, divided by 4, that's going to be equal to 4. This will be minus 32/3. And then we'll see a plus 8 at the end there. You can go ahead and distribute that 3 through. Call this 12 minus 32 plus 24. I am seeing 36 minus 32 for a final answer here of 4. A great question is how to interpret this quantity that we just found, and the answer is, yeah, I don't care.